So first of all, I would like to thank the organizers for the invitation. Actually, let me remind you about something which we have heard about on Wednesday. Gabor was talking about the 50th anniversary of QCD, which was, kind of formulated in 1973. This lecture, or this talk will be about another anniversary, which is, coming in about 200 days from now. And it was actually the moment, this date goes into the history as a moment when the physics community started speculating about possible extensions of what was then just formulated as the gauge structure of the Standard Model. And in particular, it's embedding into something simple, both in the technical and also in the, I would say, conceptual terms, simple, like a simple gauge group. So maybe you know this paper. This is the famous Georgia and Glashow paper. This was the beginning, but it was not yet physics. It's just something which served as a mathematical tool of classification of what was known about the Standard Model fields and symmetries, and it was nothing more than just noticing that what was there on the Standard Model side on the left here, actually see how little was really known back then in February '74 about the Standard Model. There was even no seq work yet. There was no third generation. Things just started popping up. Okay. Good. Things just starting popping up, and these people were brave enough to really go ahead with looking for something even better or even more compact than the Standard Model at the moment of its conception. So it's, I would say, very, very interesting and brave. So the mathematics was like just noticing that things kind of match into representations of the SU5 and nothing else. This is what the first paper is about. No dynamics, nothing, just this mathematical picture. And but there's one bit which is pretty interesting, and that's the uniqueness of this SU5 among rank 4 groups. So it's not really just mathematics, but some kind of a very good motivation to go ahead and try some dynamics. And this was just about half a year later when Georgi, Quinn, and Weinberg took it seriously, and they really started calculating in the scheme. And actually, in order to do that, of course, you have to formulate it in full glory. That requires introducing the Lagrangian. The Lagrangian is built out of SU5 irreducible representations typically. And this is something which brings extra degrees of freedom because the group is different. And if you look at what kind of degrees of freedom you need, for instance, to accommodate the gauge fields, which typically reside in the adjoint representation, then you encounter, besides gluons A and B fields of the Standard Model, you encounter extra degrees of freedom, which transforms triplets of SU3, doublets of SU2, and they have this kind of very fancy hypercharge, -5, 6, for instance, for the vector fields. For the scalars that you need, of course, to break symmetries here spontaneously, you encounter another new degree of freedom, which is like a scalar triplet, and so on and so forth. I can continue also, because you need to break also the SU5 first to the Standard Model, so you need extra fields. And there's a lot of new stuff. The interesting observation is that actually this new stuff, especially these two components, are proton dangerous. And this is a very kind of interesting observation because it opens the Pandora box of new physics. All of a sudden, you have perturbative possibility to break baryon number and so on and so forth. The immediate observation was also that not only that these fields are there, but they should be extremely heavy, which means that those kind of proton decay amplitudes which you can draw like this for the X field, or like this for the scalar, they may be very strongly suppressed and potentially, not really dangerous phenomenologically. Actually, what is the kind of observation that made them claim that those scales, those characteristic scales of the masses of those extra degrees of freedom should be very large? This is something that we are nowadays using as a teaser for our students, but like back 50 years ago, this was a Nobel Prize calculation by Gross, Wilczek, and Politzer. So I think I don't need to go through this in any detail. You should know this. So it's about running of the gauge couplings in the standard model. Of course, today we would draw something like this, but back then, of course, people knew very little about the strong coupling, about the SU2 coupling. Everything, all that has been measured to some degree, or some degree in precision, was just the fine structure constant. So the picture, okay, here you see the kind of spread of values that they were contemplating on for the strong coupling. So today, sorry, this is like a picture to today, but what they should have done was something like that, or what they did was something like this for the strong, and something like this for the SU2 coupling, and the only thing that they knew something about was indeed the electromagnetic. And now the point is that actually the masses of those new degrees of freedom, in order for this to make sense at all, should be somewhere in this band, in the band when the three things kind of coalesce eventually. And the reason is that only if you integrate those new fields at around this scale, you get a picture in which your beta functions, which are here, all of a sudden receive a universal structure, a universal form. So only if you integrate these fields in, you see the redundance of your description in terms of three different gauge factors, right? Because here all these numbers are the same. It looks like all three couplings are the same because they behave the same, but you cannot really push this further unless you start at the same point with all of them, right? So it must happen somewhere here. And this is also the range, if you go back to the old paper, where they did get some kind of first predictions for the masses of these new fields. And indeed, this is what makes these scenarios extremely attractive, because there are not that many scenarios in beyond standard model physics which tell you what is the characteristic scale. Without extra measurements. These are like low energy data that are encoded, or that we encounter like every day at the standard model scale. There's no need for any new information, so to say, to determine that, or to say something about this scale. So that's very interesting. On the other hand, the unifications are not only like about this kind of new, very, I would say, fancy phenomenology of perturbative baryon number violation, or if you want, proton decay. There are many other things that they can tell us about. Perhaps the most, I would say, solid is the charge quantization. Since simple groups have, especially, the non-abelian groups have discrete generators, or generators with discrete spectra, like all charges in those theories must be quantized, regardless of what you do, what kind of fields you throw in. This must always be quantized. Of course, you can say, charge quantization is not a big deal because we do have charge quantization to some degree already in the standard model, but it's not quite true. Or it's, what I'm referring here to is the classical game of cancelling all the gauge anomalies for like a very specific set of hypercharges which just corresponds to what we typically assume for them in the standard model. On the other hand, I mean, this nice mechanism fails when you really take into account like neutrino masses, which is, like I would say, the very first very solid laboratory-based signal of beyond standard model physics, especially if you do it in the Dirac mode. That means if you introduce Dirac masses for neutrinos into the standard model, this game breaks, and you have no charge quantization anymore by anomalies in the standard model. This has to do with the accidental conservation of B minus L. Accidental gaugeability of B minus L. If you throw in right-handed neutrinos, you can show that B minus L is non-anomalous as a global symmetry, and that means that you can actually even gauge it, and in such a case, your unique standard model hypercharge gets smeared with any, I would say, real contribution, or any contribution parameterized by a real parameter, and there's no hypercharge quantization anymore. What's interesting is that you get back to charge quantization by anomalies if you go for Majorana neutrinos. But still, this is just quantizing charges for a subset of standard model fields, namely chiral fermions, because these are the only which really do enter the anomaly game. So, for instance, if there was something like a vector-like quark or whatever, you would get no information from this mechanism. But within the unification context, you always get charges quantized, which is nice. Like another aspect of these games is the presence of monopoles. Whenever, or almost whenever you have a simple gauge group, which is broken down to the standard model, you encounter these heavy topologically stable finite energy extended Higgs gauge configurations that you call monopoles. These are, I would say, the Toft-Polyakov type of monopoles, which you can understand like a microscopic version of the Dirac monopole, like a microscopic, I would say, model. And they have very interesting properties. For instance, I mean, the Higgs wave in the center of these vanishes. And that means that the gauge fields in the center of those monopoles have essentially zero masses. And that may actually enhance baryon and lepton number violating processes in that small spatial region where the monopole sits. And this comes as under the name of the Kalan-Rubakov effect. And I will talk about that on the next slide, because all these three things that I was talking about, that means proton decay, charge quantization, and monopoles, are connected through a number of, I would say, lines. Here on the top, you have the simple gauge group structure. That means full charge quantization. Of course, like if you have monopoles, then already Dirac told us that something like charge quantization must be there. Otherwise, you would see the flux tube connecting the monopole with the anti-monopole. So this you may know about. This Kibble line is something which refers to the way the monopoles are produced in the early universe, which indeed has to do with the simple structure of the gauge group. The baryon and lepton number violation catalysis in the center of monopoles is this Kalan-Rubakov effect. And if there is a proton which hits this center of a monopole, or better to say, if a monopole passes through matter and protons, or at least quarks within protons, enter this Kalan-Rubakov area in the core, you get the so-called proton decay catalysis due to this Kalan-Rubakov effect. So these are unifications are theories of all these three things. On the other hand, it's not so easy to observe these things because, okay, you do observe full charge quantization in the standard model, but what else can you tell about that? Concerning monopoles, these are physical objects, so maybe they are accessible. On the other hand, the predictions here are such that they are extremely heavy. Typically, their masses are even above the unification scale. So for 10 to the 15 GeV, these would be at 10 to the 16 GeV, and so on. So extremely, extremely heavy objects with no chance to be produced at colliders. So typically, what you get from experiment are bounds which have to do with the Kalan-Rubakov effect. For instance, if the flux of monopoles exceeded a certain limit, we would necessarily see highly ionizing tracks in our detectors. So those limits are typically at the level of something like 10 to the minus 20 monopoles per steradian per year. So, practically nothing. And it's really difficult to hope to see something like this at the I would say laboratory-based experiments. So, in the rest of my talk, I will actually focus fully on the proton decay, on the search of proton decay, on the calculations about this thing, which is sometimes coined as the holy grail of this business. Okay, coming back to the 1974, and this Georgi Weinberg and Gleshow calculation, Quinn calculation. The situation, like the experimental situation, was determined essentially by this experiment, which was like a deep underground experiment in South Africa. Deep underground, that's I think clear because like the main background to these searches are atmospheric neutrinos. So you really need to eliminate this background to ever see anything. And like already back then, the limit for the lifetime of protons was as high as 10 to the 30 years. So something which by many orders of magnitude exceeds the lifetime of the universe, of course. On the other hand, the good thing about proton decay searches is that you can take vast numbers of protons and observe them all at once. And that means even for these lifetimes, statistically you have a certain chance to see something within the lifespan of a typical experiment, which is like a decade or two maybe. On the other hand, that number, that 10 to the 30 years, already back in the 1974, fell very much into that range predicted by Georgi, Quinn, and Weinberg, somewhere between 10 to the 11 to 10 to the 16, 17 GeV, as written in their paper, because this number actually corresponds to the mass of the mediator of a typical process like that, which enters the characteristic width as the inverse fourth power, in the ballpark of 10 to the 15 GeV. So the situation was really ripe for a discovery. And sometimes people say that everybody rushed underground and started looking for these things because, I mean, if this kind of processes were ever observed, that would be a real breakthrough in our understanding of particle physics. So in that sense, the end of 70s was something I would call the first golden era of grand unifications. And you can even see it at this kind of histogram, which is nothing but the number of papers on the archive with, actually this is with SO10 in the title. It's not about like all unifications because like people call unifications like different things. So these are just SO10 papers. And you can see that actually like there's not been that much of an activity between about 1978 in the SO10. That's why you don't see anything here. You should see SU5 papers, but yeah, SO10 is safer. And here you see the golden era. And the golden era was actually somehow, or those periods here are somehow related to our capacity to look for these processes like proton decay. And that's something which is intimately connected with the emergence or the building of large water Cherenkov detectors. So that's why I've written here like the era of IMB. This is Irvine, Michigan, Brookhaven experiment, one of the first large volume water Cherenkov detectors, which was originally built to look for proton decay. Not for, I mean, nowadays, large water Cherenkov detectors are predominantly sold as machines of neutron physics. But back then, this was driven by proton decay expectations. And of course, neutron physics was the background there. However, okay, and this is just for illustration. It's also the time when the first workshop on granifications was held in 1980, and I really like this little table, which is 13 times 13 letters, which contains the names of all participants. I'm just wondering whether it's possible to do something like that, like in workshops nowadays. Perhaps not. Okay. The next feature on this roller coaster graph is this Great Depression at the end of 80s. And actually this has to do with the first precision measurements at the SPS, which, among other things, measured the value of sine squared theta in the standard model, which, among other things, is a prediction of the minimal SU5, for instance. But the prediction is, as it turned out, is something like 20 sigma off that measurement. And that is sometimes coined as a failure of this minimal Georgi-Glashow type of the SU5 unification. And it is also the period of time when another like very famous large volume water Cherenkov experiment called the Kamiokande like came to play, and it pushed the lower limit on the proton lifetime even further by some 2 orders of magnitude to this value. So that's why like people's interest into especially like the minimal SU5 type of models kind of almost vanished in this time. On the other hand, the same kind of, okay, and this is the failure of the SU5. I mean, if you define the unification scale as the intersection of the alpha 2 in the standard model and alpha 3, with sine squared theta as measured back then, you get this point. And if you now evolve from here down to the electroweak scale with the fine structure constant, you miss this point, which is the measurement by about 20 orders, 20 standard deviations. This is also why people became a bit, I mean, as I said, became very pessimistic about this. And in 1989, allegedly, they held the last workshop on grand unification, signed by the same main editor. So it was a really desperate time. It must have been a desperate time. On the other hand, this is something which eventually started a new epoch of this kind of model building, which I just personally call the SUSY frenzy. And the reason is that the same measurement of sine squared theta from the SPS, although it refuted the minimal SU5, it indicated something very interesting, or potentially very interesting, and that was actually the compatibility of those running schemes with the low-scale SUSY hypothesis. Because if you change the beta functions in such a way that you assume that somewhere at around the TeV scale SUSY, you add gauginos, exynos, quarks, and leptons, and so on. Actually, you don't need to even add quarks and leptons, but that's a detail. What happens is this. I mean, you change the running of alpha 3 and alpha 2, and also alpha 1, and this is, I mean, what you get is almost perfect unification. So, I mean, the failure was transformed into a victory, but, of course, for the price of speculating about new degrees of freedom, and not that few. I mean, you're more than doubling the spectrum of the standard model with the low energy SUSY hypothesis. But that was the game they played those days, and okay. Another thing which happened at around the same time was where like the first potentially reliable calculations, in the sense that those initial conditions were known to like good enough precision to really try to, that it was meaningful to try to determine this point. On the other hand, there was this enormous hypothesis of new degrees of freedom, and SUSY by itself does not tell you anything about the scale, right? So, and it doesn't tell you much about the spread of the spectrum of those new fields and so on and so forth. So those calculations are reliable only to some extent, because there's a lot you have to assume. If nothing more, then you need to say something about a SUSY breaking mechanism. And there's another aspect of SUSY which is really important in this context, and that's the fact that besides those X and delta fields that I had before, that means the extra gauge degree of freedom and the extra scale degree of freedom, which entered the amplitudes like 1 over m squared because of like bosonic propagator in the graph. In SUSY, you get their fermionic counterparts. And if you exchange fermions instead of bosons, you get only 1 over m suppression in the amplitude. That means 1 over m squared suppression, where this capital M is this super large scale. So if you compare those amplitudes, the SUSY amplitudes, to the bosonic amplitudes of the original Georgi-Gleshov type, you are missing 2 powers of suppression in the lifetime. And that's a problem, because all of a sudden, although you do achieve this kind of nice unification pattern, you are totally losing on the characteristic size of those effects. They are predicted to be extremely large. Those transitions are extremely fast. By extremely, I mean the typical ballpark of those predictions are something like 10 to the 28, 10 to the 30 years. But we know already, from Kamiokande, that the lower limit is something like 10 to the 32. So, this is also the reason why there's something like the second depression. After the SUSY frenzy period, there was another depression. And that was because people realized that it's difficult to reconcile the supersymmetric account of those proton decay calculations with the experiment. On the other hand, as usual, like a depression comes. After depression, there's a period of renaissance coming. There was another renaissance, which I would put to around the end of millennium, and that's this peak here, which I would call the SO10 era, because this is also the period of time when neutron oscillations were eventually really established. The Super K and Snow made it clear that neutrinos are massive, and if you have massive neutrinos, then you need something better than the SU5 type of models. If you are ambitious to describe the neutrino masses. And SO10 is that kind of a theory, because unlike in the SU5, where you typically confine or collect those 15 those 15 fields of one fermionic generation of the standard model into 2 irreducible representations, in the SO10 has got a 16-dimensional spinner. And if you look at this 16-dimensional spinner, it contains, besides all the standard model matter in one generation, also a right-handed neutrino. And this is the basis of the implementation of the seesaw mechanism. So, in a sense, SO10 paradigm replaced the SU5 paradigm. And there's more to that. In the SU5, you typically have very little freedom to fiddle around with scalar fields, for instance, or to play with the scheme, simply because SU5 is rank 4. And there are very limited options how to break it to another rank 4 group, which is the standard model. In the SO10 case, that's a rank 5 structure. And if you have rank 5 and you need to break it to rank 4, there's plenty of room for playing nasty games, I would say. And this is what people did. And one of the outcomes of such games is that you kind of earn more room for the suppression of, if you like, a suppression of the amplitudes of those BNL violating processes. So that's why I will devote the rest of my talk to DSO10. On the other hand, like with those larger and larger unified groups, there's the issue of calculability, which immediately pops up. And it has to do with the number of degrees of freedom that you need to really put this into life, to formulate a potentially realistic model. And we will see it at the, at a specific construction that I will talk about in a minute. But first things first. So, concerning calculability, this is not an academic thing. I mean, it's a very practical problem, because if you go into the literature, into the more modern literature, and you look at the error bars for the predictions of like the lifetimes in different channels, you encounter a situation like this. So, like the precision of those predictions is stretching over 12 orders of magnitude. This makes absolutely no sense, like from the experimental point of view, because, typically with each new generation of those water Cherenkov detectors, you gain, at least like lately, you gain something like 1 order of magnitude in precision. So here, for instance, there is a comparison of the Super Kamiokande reach, which is something which we have as the best limit nowadays at the order of 10 to the 34 in this golden channel of proton to E plus pi 0, or here proton to nu k plus, compared to the next generation, which is hyper K or Dune. And here you see there's the improvement window, or the improvement margin, if you like, is only about 1 order of magnitude. So what would you ever learn from such an investment into the new technology if your theory is as bad as like predicting these numbers with the precision of 12 orders of magnitude? This is a nonsense, right? On the other hand, there is a reason for this. For this bad theoretical situation, because there's a number of, I would say, uncertainties which enter those calculations, which have to do with many aspects of the business. The classical showstopper used to be the Hadronic matrix elements. It's only like relatively recently that we have got good enough technology to calculate these things, especially the baryon number violating matrix elements, which people do not invest so much time into compared to the other QCD stuff. On the other hand, there's been some progress on these, and the situation is getting better and better. In this sense, I would even say that we should strike now. Now should be the good time for this kind of calculations, not before. There are other things, as we have seen. The accurate determination of the gut scale is important for for the precision of the calculations, because it enters a lifetime as the 4th power. So whatever error you do there propagates with large power into your prediction. And I will talk about that in a minute. The other thing is that, for instance, we are lacking information, or mainly, or in typical cases, we are lacking information about the flavor structure of those charge currents which are beyond those processes. These are charge current processes, obviously. And there is, like, typically, if you write the effective Lagrangian, you encounter something like an analog of the CK matrix that you have in QCD. And you have very little information, typically, about these flavor structures. On the other hand, as I said, the situation concerning, for instance, the Hadronic matrix elements improved considerably in the last decade. This is a paper from 2014. I'm not sure whether there's something better, presumably yes. But already here you can see that the relative error of these calculations I mean, was like considerably, I would say, reduced, so that this does not need to be a showstopper anymore. I mean, if you are aiming at something like an order of magnitude precision in the proton lifetime prediction, I mean, these numbers are pretty fine already, because, I mean, there's something like factor of 2 at most in the hadronic matrix elements, so factor of 4 in the lifetime. So this is pretty good, but this is recent. Concerning the flavor structure of those charge currents, I mean, this is a little illustration of how things work, or better to say, do not work in our favor typically, because what you typically encounter in those effective dimension 6 operators that you can use for the effective description of these processes are flavor like structures like this, and you see, I mean, this D is a unitary matrix which diagonalizes the down quark effective masses from the left. So this is something which we know at least a little bit about from the CK matrix. This is the same structure which enters the CK matrix. On the other hand, this guy, that's the right-handed rotation. And if you encounter right-handed rotation in a flavor structure somewhere, you are totally lost, because we know nothing about those right-handed rotations from the low energy data. On the other hand, you can cheat this problem a little bit, especially in the SO10. You often encounter a situation when your Yukawas, I mean, the part of the Lagrangian which defines the flavor, I mean, is symmetric in the flavor indices. And that means that the left-handed rotations and the right-handed rotations are tightly connected. So if you focus on some kind of minimal models, you may have a chance to overcome this issue. But you really need simple Yukawa sector. That means you need to choose your scalars, which are supposed to break the gut group down to the standard model pretty carefully, because those are typically also the scalars which define the Yukawa part of the Lagrangian. What's kind of interesting is that some channels, like especially the neutrino channels, are typically more flavor robust than others. And the reason is that you do not measure the flavor of the neutrino in the final state, and you typically need to sum over these flavors, and due to unitarity of these matrices, you sometimes kind of encounter cancellation, or better to say, the unitarity conditions on these, that these matrices here obey, give you something. I mean, typically some zeros or ones, and that structure simplifies a lot. So this is the kind of games that people usually play, and okay, I will not talk about that anymore. What's really crucial, however, I mean, as I said, is the accurate gut scale determination, because that's something which enters as the fourth power into the lifetime. And here, we can do almost nothing about it, except for calculating better. And by better, I mean, one should really calculate at least at 2 loops. And the reason is that if you calculate at 1 loop only, then you typically encounter, I mean, those two curves, I mean, this is alpha strong, alpha 2, they typically intersect under a pretty shallow angle in the log plot, right? And due to this shallow angle, it's difficult to kind of get like the good or precise location of this intersection. And it's not even this intersection which defines the masses of those mediators. You have to do way more than just kind of looking at the picture and like searching for the intersection. The other thing is that here there's a plenty of new states. I mean, those extra gut states, which one should take into account. And like a simple intersection makes really no sense. You should really better understand the entire spectrum there. That means you should really go, diagonalize the full gut Hamiltonian, get the masses, and only then you can play these games. And there's yet another problem with like good gut scale determination, and that has to do with something I would call the gravity smearing effects. I mean, if you have a scalar which receives a vacuum expectation value which is very close to the Planck scale, and you encounter such an operator at dimension 5, then what this does is, in the broken phase, this is like a kick to the gauge kinetic form. And the kick to the gauge kinetic form requires canonical normalization, and that's a redefinition of the fields. And that also comes with a redefinition of the meaning of your of your alphas there, those gauge couplings. But you know nothing about those kicks, practically nothing, because this can come from gravity physics, right? And it's inhomogeneous, and you really don't know what this lambda is, you don't know what this kappa is. And what's interesting is, if you translate this into the game this kind of looking for the intersection of the two curves, what you encounter is this. So forget, if these effects are there, then it doesn't make sense to calculate anything at all, because you cannot really determine the key input of your calculations, and that's the gut scale. However, I wouldn't be here if the situation was this bad. So let me show you what one can do in the realm of the SO10s. There's a workaround concerning those gravity smearing effects. Unlike in the SU5. Actually, the rule of thumb here is that you should select your gut-breaking scalar in such a way not to be in the product of two adjoints of that given symmetry. In the SU5, that means that you should select the Higgs, or that scalar, in such a way not to be 24, not to be 75, and not to be 200, because these are the components in the symmetric part of the composition of that product. However, in the SU5, this is a problem, because these are typically those representations that you have to employ to break the SU5 to the standard model, because here the rank is 4, and you cannot really throw in whatever you like, because typically you break the rank if you just go for a random scalar. The situation is better in the SO10 in the sense that, these are again the usual suspects, which you really better not encounter, but there's a more minimal choice of the scalar sector in which you can avoid these fields, and if you do, then you do not suffer from those gravity smearing effects. And only then you can have a chance to calculate something with a better than 10 orders of magnitude precision. So in the rest of my talk, I will focus on one of those specific schemes. I will tell you the story of the minimal SO10, because this is allegedly the minimal, reasonably calculable gut around. So what's good about the SO10? Just very briefly, I already told you that there is this 16-dimensional spinner. It nicely accommodates everything in the standard model, including the right-handed neutrino that you need for the seesaw. And there is a seat of the SO10 structure already here. It's just a matter of a bit like a few reshufflings. So the first thing that comes to mind is actually to come up with something like an SU2R, because now your right-handed fields are ready to be embedded into doublets. In the presence of with the presence of the right-handed component of neutrinos. And indeed, you can do it, because if you look at the hypercharges here and B minus L, for instance, over 2, the difference between this number and these numbers for the right-handed fields correspond to the third components of a new isospin, essentially. So it's very natural to group these right-handed fields into an SU2 of some kind. And this SU2, I would call it the SU2R, because it acts only on the right-handed fields. And all of a sudden, you get something pretty nice, and that's, this is the formula for the hypercharge, for the electric charge in the standard model. This would be the hypercharge in the standard model. In those left-right symmetric theories, you give a very nice physical meaning to B minus L, for instance, in terms of the electric charge. Okay, so that's the upgrade you typically do. But you don't need to really stop at this place, because you can take this SU3 and the U1B minus L that we have just identified and go further. And just by kind of noticing that SU3 times U1 is a subgroup of SU4, you can actually unify these two factors into an SU4, which is typically called the Patti-Salam symmetry. In a sense, it's a reinterpretation of the lepton number as the fourth color. That's the kind of jargon. And from here, it's only one more step to the SO10 because SU2 times SU2 at the, this is a subalgebra. Sorry, this is isomorphic to SO4. SU4 is isomorphic to SO6 at the level of algebras. And if you have SO4 times SO6, you are there at SO10, right? That's obvious. So that's why SO10 is a very nice option in this gut model building. On the other hand, as I said, the SO10 has got larger representations than the SU5, and it's really like a model building maze to choose some nice scalar sector which would eventually give you everything you need. That means the breaking to the standard model, the Yukawa sector, and so on. So it's a maze. It's a really model building maze. And you need always at least two fields. Up to some single case, you need always at least two fields to really do it. And here you see this 54, 210, and so on. They are a priori discarded because those are the fields which would bring you all the trouble with the gravity smearing effects. So you have to do with something else. And if you look at this maze, this is some kind of a scheme from this paper. You encounter one pretty interesting thing. You can live with 45, the adjoint, but a scale in the adjoint representation. And this 45 is enough to break the SO10 to the SU3 times SU2 left times U1 R times U1B minus L. So almost all the way down to the standard model. And there's a need of only one more representation, which eventually reduces the rank, because this is still rank 5. By the way, you probably know that with an adjoint scalar, you can never break the rank. That's why we are stopped here from rank 5 to rank 5, and we need something more. And this something more is typically something like 126 or a 16-dimensional scalar. There are two VEFs in this 45 multiplet, and depending on their hierarchy, you may arrive at different intermediate symmetries and so on. But the main observation is that the gravity smearing effects are absent in this case, because you cannot simply write down such a thing at dimension 5 to the SO10 Lagrangian. So this is like the first prerequisite for a better than 10 orders of magnitude prediction of the proton lifetime, and we can take it out. Concerning the structure of this 45 scalar representation, and those different paths that you can go from the SO10 to some smaller intermediate groups, you can see readily that if those two VEFs are the same, then you are homogeneous in a 5-dimensional space, and this 5-dimensional space corresponds to the SU5. So you arrive to something that we have already discarded before. So this is maybe not the best thing to do. If they are not the same but just comparable, that's, I would say, the general scheme with the SU3 times SU2L times U1R times U1B minus L I was talking about just on the previous slide. So that's, I would say, the most general case. There's also the case when these two have opposite signs. This is called the so-called flipped SU5. I will not spend time on it. And in case that these two VEFs, these two types of VEFs are hierarchical, then you encounter other symmetry limits, like this is the left-right model, and this is something like the SU4 of the fourth color times SU2 left times U1R. So there's a plenty of things you can do with 45, but you stop at rank 5 because that's the adjoint. So you have to do something more. I can right away discard these SU5 unifications because they are sick, as we have seen. But it's not the whole story. You need something like 16 or 126 to reduce to rank 4. And if you do it, and you look at those two options, the 126, although it's a bigger representation, is better for the model building because it makes it possible to keep the model renormalizable. With 16 only, you cannot, for instance, do Yukawa. I mean, you cannot create a Yukawa sector which is realistic at the renormalizable level. It's a technicality. On the other hand, this 45 and 126, although they are large representations, I mean, they are really those which define the minimal renormalizable SO10. You can write down a renormalizable Lagrangian, which looks like it's ready to give you everything. On the other hand, it's a nightmare. This is the scalar potential only. And I mean, those fields with 5 indices, those are the 126 components. The fields with 2 indices, those are the 45s. And if you count all these terms there, like summing over all those indices from 1 to 10, you encounter something like 10 billions of different terms. Although they are all parameterized with just like a handful of couplings, something like 12 or 13 couplings. So here we are encountering minimality in terms of the number of parameters rather than, of course, the number of fields. But for the predictivity, this is the key. So it's a nightmare rather than a minimal model, but you have to live with that. On the other hand, like if you really go and do the homework, that means you diagonalize the Hamiltonian, you calculate the masses, you do what you should, you encounter something pretty nasty, and that's a tachyonic scalar in the spectrum. So there are two, I would say, pseudo-Wilson bosons in the spectrum which have some pathological features. In particular, regardless of how you choose the omega R and omega BL or omega Y, as we call it before, one of these will always be tachyonic. And that's an indication of an unstable minimum, and you cannot really calculate around that. So it looks like, actually, there is only one potentially stable minimum, and that corresponds to that cursed SU5 type of a scenario I really don't want to avoid. And maybe we are doomed. Actually, this is a pretty old observation already in 1983. And this is what put those models, this minimal SO10, to oblivion until about 2010, when we kind of took it somewhat more seriously, and following the second Weinberg's rule of progress in particle physics, that you should not trust the three-level calculations, we have redone this analysis at the one-loop level. That means we went to the quantum regime of this minimal SO10. And what you encounter, of course, it's a super nightmare now. But there are nice techniques how to deal with these things, like the effective potential and so on. And the main observation is that the situation changes very dramatically because the radiative corrections can save you from this trap of the tachyonicity. In other words, the radiative corrections like convexify the potential in that critical minimum that you want to sit in to such a degree that you can really live and be stable there. On the other hand, this is not yet a win, because if you really want to calculate something, you should do more. But that observation itself kind of unblocked these three chains, and we were happy, but actually not for long. Because if you want to really do calculations, there are other problems you have to overcome, and one of them is actually the problem with the seesaw scale, which turns out to be problematic here, because like seesaw scale typically wants to be somewhere in the desert between the electroweak scale and the gut scale. This is the typical picture you get in the SO10. You cannot do this in SU5 because you don't have the intermediate scale because of the rank 4 situation, but here you can. But if you have this kind of big hierarchy between the gut scale and the seesaw scale, there is a problem with perturbativity. And the reason is that actually the fundamental parameters in the Lagrangian, in terms of those VEFs, are given like, I mean, there's a typical combination that you get. This is omega R, omega Y, or BL, as we sometimes call it. And sigma squared makes it to the denominator. So if there is like a big discrepancy or big gap between the gut scale, which is one of these omegas, and sigma, this term tends to blow up. On the other hand, you don't need both these omegas to be at the gut scale. It's sufficient to have only one of them and be in one of those hierarchical regimes. And that's the only solution here to the perturbativity issue. So those omegas really must be, by phenomenology, must be very hierarchical. And it means something, again, to this classification, it means that you are not allowed to go through this regime, through this intermediate symmetry. So there are only two options left, this SU4 or the left-right. And you should better go and look at them very carefully, because now the number of potentially realistic options is shrinking. So that's what we did in this paper like a year ago. What we did actually was we looked at the perturbativity features of this, because this model contains a lot of fields, and you really have to be sure that your perturbative account of the quantum level calculations is kind of consistent. And what we did was, we calculated, among other things, like the beta functions for all couplings in the scalar potential. And you can see, there are like enormous coefficients, which of course have to do with the normalization, but still, like this defines a renormalization group flow, which may be pretty turbulent or like very divergent because of those large coefficients. And indeed, there's no trivial fixed point here, because there are gauge couplings. Like there is a gauge coupling, and we know that the gauge coupling is not zero. On the other hand, these are exactly like those quasi-fixed points that you should identify as like those potentially realistic parts or potentially perturbative parts of the parameter space where it makes sense to really calculate. Okay, so yeah, there is a number of them. And that's what we did. Actually here, what you can see are the like different cuts of this multidimensional parameter space where those different points are displayed, and the color code corresponds to the kind of perturbativity range that you can encounter before something explodes in the RG flow. And in particular, those red points are the most promising ones. So you see, there's nothing like 0, 0, the trivial fixed point. You have to be out of 0 in order to really thrive in some way. And the interesting thing is that for this SU4 times SU2 times U1 scenario, you get a relatively like stable points with the perturbative kind of range of over more than 3 orders of magnitude, which is pretty fine for the gut scale. But you get nothing like that for the left-right, right? Here you encounter something like 1.5 orders of magnitude, which is pretty, tight. So you can actually project it back to this classification and discard this at least partially because of the perturbativity reasons. So eventually you come to the conclusion that there's only one option how to break the SO10 in a calculable way, and that's this piece. And this is my last slide. Actually, this is about a very recent study that we have posted to the archive just a few weeks ago, which discards even this option. And the reason is that, in order for this kind of models to work not only in the scalar sector, but also like for the flavor, you need to smear one of the degeneracies which you typically encounter in the SO10, and that's the degeneracy between the masses, the effective masses of down quarks and charged leptons, right? And that smearing is due to the, I would say, non-zero, or I would say significant contribution to the effective masses from the 126 scalar component in the low energy Higgs. And if you cannot make this number kind of comparable to this number, these are the weights of the 126 and the 10-dimensional scalars in the low energy effective Higgs doublet. If you cannot make this number significant, then you cannot really distinguish, take apart the masses of tau, for instance, and bottom. So that's one of the phenomenological, I would say, requirements that you have to better obey. but the model does not admit it. And that's pretty interesting. I mean, this is the perturbativity domain in one of the cuts of the parameter space as we had it before in those diagrams. But the realistic flavor domain, that means a domain which can support a significant 126 portion, is only here. So here you see an incompatibility between these things. Of course, there's a lot more about this in the paper, but the bottom line is clear. I mean, this is the death blow to the minimal SO10, in a sense that we have one after another discarded, at least at the perturbative level, all those possible symmetry breaking patterns which were compatible with the absence of gravity smearing effects. That means with like the breaking being dominated by the 45. And here we are now. So what I would say is that the field now, I mean the gut field is on the crossroads now. And the reason is that essentially all the minimal renormalizable guts, by which I mean the minimal SU5, the minimal SUSY SU5, the minimal SO10, and also the minimal SUSY SO10. I mean, I didn't have time to talk about that one, but there is a very similar story to something I've said before concerning the minimal SUSY SO10. All these four scenarios are dead now. And the question is what to do next. Maybe it's time to reconsider the ambition of having a unified, a grand unified extended gauge symmetry. Maybe it's sufficient to embed the standard model gauge group into something which is slightly smaller, maybe not like a full-fledged simple group, but something like 2 factors, for instance, and so on and so forth. Okay, so thanks a lot for your kind attention.